it's about simulation modelling, but it's specifically about the models in JKSimMet, and that's simply because my background from way back is JKSimMet modelling. And in my view, and I think if you could talk to any comminutors around the world, it is the only simulator for comminution. There is nothing else that gets anywhere near it. And that's not because I was involved in it from way back in the 1980s. It's just that I know the models in there, and I know the models in all the other simulators, and the strength of JKSimMet is in the models, and the huge amount of work that went in, mostly from students doing masters and PhD theses to develop those models. That's not to say there aren't other good models out there, but in terms of a simulator with a collection of models, it's the best there is. And I'm going to talk about all of those models, and my focus is going to be on not so much where it's difficult to use them, because there are cases in the sense that you as the user of the simulator have to put in certain parameters, and as an engineer then you've got to make the decision, what number do I need to put in? Those numbers can be obtained if you have a lot of data yourself. If you don't, and in a greenfield situation, often you don't have that data because obviously the plant's not being built. I'm going to talk a bit about ways of how you can get that information so that you don't have to worry about the parameters you're putting in. And you'll see the thread all the way through this presentation. Not only will the models that I've talked about before be coming up on the SMC test website, these, for those of you into gaming, these cheats that I'm going to talk about are also going to be up on our website for open use. And they'll basically be saying, if you're using JKSimMet and you want the best parameter for a design situation, basically, here's the number that you can use. And there'll be a whole host of them. And I'm going to talk through all of those as we go through this presentation. 4 sets of comminution models that I'm going to talk about, and every single one of them uses what's called the population balance model. And JK definitely did not invent that equation. It's been around for a very long time. It is a beautifully elegant equation. And even if you're not good at maths, just take the trouble to try and understand this equation. It's been attributed to a guy called Epstein back in 1947. It is elegant. It is just simply a mass balance across any comminution machine, and it's a mass balance that goes through size by size, and its elegance is in its simplicity. Basically, it says what comes out is what goes in less what's broken, which is obvious. That summarizes all comminution machines, and it does it on a size by size basis. I is a size fraction, and the model works from the coarsest size fraction all the way down. And in a computer algorithm, the computer basically steps through the coarsest size, and it simply goes further down and further down and further down, breaking until the whole distribution is broken up. To do that, the model requires some information about the feed, obviously. Most of the times we're interested in the model predicting the product size distribution. So if we take this particular case here, if we can give it the feed distribution, and if we can give it this term here, that's the breakage rate or the breakage frequency, and we can give it that term there, which is what's called the appearance or breakage distribution function, we can do something about predicting that. Now you might just say to me, Steve, you've forgotten S, that's the load. I haven't forgotten it, because what basically happens in all the subsequent models that we're going to look at, they've been modified to the point where you don't need to worry about that. It effectively disappears, and you end up with a much reduced equation. One of the biggest contributions to Ag and SAG-mill model, believe it or not, is this innocuous looking little equation that Professor Whiten from the JKMRC put together. Now, what this enables you to do, I know it's given us another parameter, the discharge coefficient. It enables us to say something about material transport. Where in that equation does it say anything about material transport? Nothing. And that's its deficiency. There's nothing in there about how slurry flows or particle flows or anything like that. So, big problem if you only have that bit of the equation. Bill Whiten said, well, here's a very, very, very simple equation. And this allows us to introduce certain rules to do with transport. For example, in a crusher, the simple rule might be, if the feed going in is bigger than the open side setting, it's going to be crushed. If it's smaller than the closed side setting, it's going to pop out the bottom of the crusher. Now, I know I'm verbalizing that, but you can easily put that in a series of 2 or 3 equations, and that can be coded up in that form. Very, very powerful indeed. So, what are the pros and cons? Exceptionally versatile. That population balance model will just about fit any comminution device you care to mention. As somebody once said, it is so versatile it could fit an elephant. It's that good. It's easily understood. It has a highly systematic structure. Its biggest Achilles heel, you need a lot of sub-models to give you all those parameters that I said you need to put in. The principal submodels are the appearance function. You've got to give it that. The breakage rate. You've got to give it that. The transport function. Well, I've just shown you the function, but you've got to also give the parameters in that transport function. So as a modeler, that's what you would be faced with if you wanted to develop, for example, a Ag or SAG-mill model. At the end of the day, however, at least this one, that's not that difficult. And that's what the drop weight tester was developed for. An appearance function is a size distribution. It's as simple as that. Nothing fancy about it. And it's the size distribution that occurs after you've broken a rock. The drop weight tester was developed so that it could break just about any size rock that we see going into a comminution device. The way that the appearance function is handled in your model is through this T10 parameter. Remember what I said before, I'm not going to go into too much detail with this because I understand the concept bothers some people. This is a product size distribution from a crushing event. In this particular case, it was a 10 millimeter particle. The T10 is the percentage passing 1/10 of that original size. Well, 1/10 of 10 is 1. So we come up there, go across here. The T10 is 45. So 45% of that original rock passed a 1 millimeter sieve after it was broken. Again, you might say, yeah, so what? Well, if I increase the energy of that crushing event, I'll get a finer product. There it is, there's the finer product. I've increased the energy. The T10 now is 55, not 45. It's gone up as we would expect it to. All you need to remember is that in our model, if we can somehow relate the energy to this T10, then sitting in all the JK models is a way of going backwards. And what the algorithm does, if you give it the T10, it basically goes back along this line and generates that entire size distribution. And the guy Narayanan back in 1985, that was his PhD thesis. That's what he got his PhD thesis for. There's a map that sits in some JK models, and that map enables the algorithm in the model to take a T10 and give the entire distribution. And that actually was really smart. It's a very, very smart thing to do. And that's the key to at least the AG and SAG mill model. Let's look at, for example, the AG and SAG mill model. And if you remember, this should be familiar to you when I looked at the raw JK drop weight test data. The drop weight test is known mostly for being used if you wanted to AG and SAG mill simulations. And you get out of that drop weight test that line there, which gives you an A and it gives you a B. And inside the AG and SAG mill model, there's an algorithm which calculates for each particle size how much energy is actually used to break it. And that map sits in JKSimMet. Each size fraction is assigned an energy. The energy goes into that equation. You as the engineer have given it the A and the B. It spits out a T10. And if you remember what I said before, the algorithm works backwards to generate the entire distribution as the appearance function. Very elegant. Let's look at breakage rates. Breakage rate, if you don't like the term breakage rate, and I don't, and it was part of my master's thesis to look at it in a different way. You can think of it, if you like it better than that way, it's the collision frequency. It's the frequency with which breakage events occur. So if you can put your mind into an AG and a SAG mill, you can see where those balls are hitting a particle and breaking it. It's the number of those per hour or per unit time that are happening. That's what the breakage rate is. And it varies with particle size. Particle size is on the x-axis and the breakage rate is on the y-axis. This fully developed curve here is what we see just about in every single AG and SAG mill. If you do a survey of an AG and SAG mill in the field and you gather the product and the feed size distributions and you put them into JKSimMet, SimMet model will give you that breakage rate distribution. And you can divide that distribution into two parts. The coarser side, that's grinding media, and this curve dictates how quickly that grinding media is ground down. The faster you can grind down all those big rocks, the more throughput you can get, because that grinding media basically builds up in the mill. It's a load. And if you can grind it down quickly, you get more throughput because you give more space for the feed to come in. So this part of the curve, from a modelling perspective, controls throughput. This side of the curve, that slurry sized particles, this side of the curve dictates grinding of the fine particles. If we look at ball mills, you see exactly the same curve, but ball mills don't have really, really coarse feed, so you never see this part of it, but you definitely see that shape there. Going back to AG and SAG mills, let's say this curve here comes from running my mill in a particular condition. Let's say it was with AG, no balls. And then I did a survey, got the breakage rate distribution, and then I put in 15% balls in the mill, and I did another survey, and I got the breakage rate distribution. What we'd see is a completely different shape. It would be like that. And the trick in modelling is to be able to develop equations that describe that change from there to there, and from there to there, and from there to there, describe it in terms of what I actually did. In this particular case, it's ball load. And that is what the variable rates model, which was developed back in the 1990s and still is the most popular AG and SAG mill model there is. It still sits in JKSimMet. The background behind it is that it was developed, the framework, by a guy called Cam Leung in 1987. So he developed the structure and it's still in the simulator. He, however, only got as far as saying, I don't understand why the breakage rates changed. They'll have to be fixed. I'll leave that problem for another student. He was a PhD student, and there's only so much you can do in one hit. And so he just got the structure together, and he was awarded his PhD for that. And he had a very, very, very simple transport model in there. I did my master's thesis in 1989. I joined in 1987. My master's thesis was to evaluate that PhD. And I was awarded my master's thesis in 1989. I did a lot of my work at Alcoa. Remember that name because it's going to come up later. I got on staff of the JK Centre, and I was asked to work with a master's student called John Matambo. And I got John to go through all the JK's pilot data and fit breakage rates and try and get the beginnings of an equation that related breakage rates to operating conditions. My PhD thesis was in power draw modelling, which I got in 1994. So we added the power to the AG and SAG mill model. I then took John's pilot rates and added ball size, mill speed, mill diameter, feed size and recirculating load into those equations. We then calibrated it to full-scale data. Also in 1994, I started looking at the transport model, and I had an honours student, Ian Stevenson, and in 1994 he got his honours thesis by putting together a very simple great flow model, and that model is still in the JKSimMet variable rates model. That's as far as development got, and that is the model, the variable rates model that currently sits in JKSimMet. Between 1994 and 2000, I worked with Sanjeev Lachareddy. He was my PhD student, and we expanded that model significantly to encompass pulp lifter design, size, and we did a lot of pilot work and a lot of full-scale work to improve that model. I left the JK to do my own thing in the year 2000, and unfortunately nothing further was done on that work. One of the patches, I remember, or cheats as I call them, is that I've recently taken all these data and put together an equation that links all this work to the model that currently sits in JKSimMet. The model that sits in JKSimMet asks you to put in a discharge coefficient. It's your job as the engineer to put that number in. What this cheat does, effectively, or will do, you'll be able to put in pulp lifter size, grate open area, pebble port size, a number of other things. It will then tell you what that discharge coefficient should be, and you can then manually put it into that JKSimMet variable rates model to enhance the existing model's capability. Now, don't pester, please, JK Tech, those of you who have JKSimMet, to say, oh, why isn't it in the model now? It's not their fault. They are actually working towards upgrading all of their models, and we are talking together at the moment about the possibility at some stage, and we don't know when that is, of having this coded in JKSimMet, so you basically won't have to look at it offline. But in the next couple of months, that cheat will go on the SMC testing website. Right, ball mill modelling. Bill Whiten, 1972, also at the JK Centre, put together what he called the perfect mixing ball mill model, and that is the model that sits in JKSimMet at the moment. It was specifically designed for you to optimise your ball mill circuit. It was not designed for you to use in a greenfield situation, and I would strongly recommend it is not used by you if you are a simulator for those circumstances, because it was not meant to be used for that. One of its problems is that the breakage rate, remember that distribution I showed you earlier, the model doesn't give you that. You as the engineer have to provide that breakage rate distribution. So you're faced with that dilemma. Well, where do I get it from? And the advice is, well, you need to get it from a similar circuit or from a pilot mill test that you've done on that ore, and then you use JKSimMet to fit those rates, and they're plugged into that model. And the model inherently has some scaling factors depending on dimensions, as you see here, ball load speed, slurry flow rate, bond ball mill work index. Ball scaling also, size of ball, that's something I added to it back in 1999. The problem is, in design, what is a similar operation? And similar ore, well, if you don't have an operation with a similar ore, then you're stuck. And the other thing is that from all the pilot data I've seen, compared to full-scale data, the shape of that breakage rate curve is different. So you basically can't use it for pilot scale up. So don't use it in its current form for design. Optimization, fantastic, because that's what it was used for. Just as with the AG and the SAG mill model, I've been spending quite some time looking at ball mill breakage rates, and there will be, in due course, another cheat where you will be able to put in your ball mill conditions. You'll need the MIA, if you remember that came from the SMC test, and the MIB, that comes from the ball mill work index test. And that cheat will give you the rates that you have to put into the JKSimMet model. So it'll tell you what you need to do. Excuse me. And the cheat is based on this relationship that we've come up with. This is the breakage rate versus diameter mill relationship. Don't ask me why they are relatively straight. It was a pattern I found as I was looking. I was looking at pilot data, looking at full-scale mill data of all different sizes. And this parameter I determined, which was based on the power draw and ball size and so on, I was intrigued to see this line. Wow, that's good. And so I have the equations for each of these, and they're what are going to be sitting behind this cheat that's going to be on SMC testing website. And effectively, those equations for those lines, each one of these lines is for a different particle size. And they will generate these data points, which is what JKSimMet wants you to give it. So you'll put the data into SMC testing website and it'll tell you what these data points is, and then you should be able to run a reasonably good simulation of a ball mill circuit in a design situation. Once again, there's Bill Whiten again. Bill did a lot of really good work in the early 1970s. Bill also took the population balance model, he stripped it down, and he put together what most people, even outside of the JK Centre, says is the best crusher structure that there is. And the way it works is on a repetitive cycle. It goes crush, separate, crush, separate. The separation bit is, remember what I said about transport and making a little algorithm? Bill's algorithm basically says crush, here's the appearance function. If the material is bigger than the closed side setting, it stays in the mill. If it's smaller than the closed side setting, it pops out the bottom. And that's what his crusher model is. In JKSimMet, you'll find that Anderson-Whiten crusher model is the one that's normally used. And Jan Anderson was a master's student when I was, and I shared an office with him. So I know that model inside out because he developed it. It was fitted and validated using a database of 7-foot cone crushers, and it works very well for 7-foot chrome crushers. And he also put in a power model. The problem is no further work was ever done on it because effectively funding from industry, and the JK was always industry funded. It never used to get any government money. And if industry didn't fund it, then the research wasn't done. Industry stopped being interested in crushers for whatever reason. And so we never ever did any more work on this. So we didn't look to see if it can be extended to secondary or primary crushers. Experience has told us that there appears to be some strong trends depending on the parameters of that model, depending on whether it's primary, secondary, tertiary, or pebble crushing. So from a design situation, once again, the model is quite limited because, again, as an engineer, if you're using JKSimMet, it's your job to put the parameters in. And if you don't know what they are, then you can't use the model. So, yet again, another cheat. There'll also be a series of pages on the SMC test website. If you give it the MIC, it will tell you the Anderson-Whiten crusher model parameters that you need for primary, if it's a primary crush, secondary, tertiary, pebble crushing, and so on. So once again, it'll enable you to be able to do something in the design situation. This is the accuracy that tested it against primary crushing data that I have. These are pebble crushers up here, and primary crushers are down here. All right, just to finish off the simulation modelling one with HPGR. That's a model I put together with Luis Tondo, as a Brazilian student, and Frank Scher, who was a Chinese student, became on staff. We published this model in 1996. Once again, it's a modification of a crusher model. It was never designed for design. It was a scale-up model. And in 2004, my master student, Mike Daniel, took that model and worked out that it actually worked very well scaling from laboratory HPGR to full scale. What he did say, the throughput model was not that good. So that's the model that currently sits in JKSimMet. Yes, this looks a bit ugly here. That is the, if you like, the structure of the model. It looks quite complicated, and it comprises, the whole model comprises a number of submodels, and it makes the assumption that big rocks in an HPGR have to go through some pre-crushing. The big rocks are nipped by the roll and crushed. Those rocks then find their way into a packed bed in here. So there's a packed bed crushing model. And if you know anything about HPGRs, there's very little packed bed developed on the edge of the rolls. It's called the HPGR edge effect. And the product out of an HPGR from the edge is very coarse indeed. And it's because the pressure doesn't build up enough on the edge. So we've also got what's called an edge crusher. What we ended up with, unfortunately, and this is my model structure, is we had a model with 19 parameters, which is like, oh, goodness. The reason for that is the two principal sponsors of this research were HPGR equipment manufacturers, and they believed strongly that these processes were very important, and if our model that they were paying for didn't include them, then for all intents and purposes, we weren't getting paid. So that's why the model looks so complicated, and in actual fact, that is what goes on inside that crusher. At the end of the day, experience has shown us that most of these parameters, they're not variable, they're actually constants. So you can cross most of them off. You can put constants in there and you end up with somewhere around about 3 that you need to put in, which is much better. So you can ignore all this pretty stuff up here. I don't know whether it translates into Spanish, but we call this window dressing. So that's all window dressing there. So to carry on with that theme of cheats, yes, also with the HPGR model, there will be some cheats for the HPGR model in due course, and those cheats will use the SMC test MIH and the SMC test MIC as well to get that done. So what about the accuracy of that HPGR model? Well, I've got a lot of pilot data which nobody's interested in pilot and lab data. Fortunately, these three operations have published over the years a lot of data, and I was able to use it to actually test that model out as if I didn't know anything about these. So I took their feed, hardness and so on, and simulated what their circuit should do. Serra Verde was, I think, one of the first full-scale HPGR circuits ever. Boddington was the second, and Tropicana, no, it wasn't the third. They're the three that I've got information from. And you can see here, it predicts the tonnes per hour really well, kilowatt hours per tonne really well, and the P80 really well. So I'm reasonably confident that it'll give you good service if you want to use them. Okay, that's simulation.